In this section, we are going to focus on something known as transfer learning. And as this icon suggests, you can take a reasonable guess as to what it may be. So far, you've built deep learning models, and we built the said deep learning models from the scratch. And we defined our deep learning models using Keras, and then we implemented those on our data and we tested the performance, and we saw that deep learning can be quite powerful. But the thing with transfer learning is, as you can see, that someone's giving their brain to the other person. We can actually sidestep the step of creating a model from the scratch. So transfer learning is a method that uses a pre-trained model for a task. So we have the inputs, and the inputs are all ours. But instead of training a model from the scratch the way we did in the previous section, what we have is a pre-trained model. And this starts as a starting point for model development for some other task, say image classification, and an already trained model acts as a jump starter for one of the development processes of a new model for another task. So instead of creating the deep learning models the way we did previously, we have a pre-trained model which acts as our starting point. And why would we even want to do it? Is it laziness? But actually, no. Most applications require very large neural networks to train. So what we've worked right now, we've just scratched the surface of deep learning with a couple of inbuilt images, a couple of images from other sources. But in the real world, especially in the world of finance, medical imaging and all, we have a massive amount of data which requires huge neural networks to train. And neural networks, they in turn require a huge amount of data which already is there in things like medical applications and computational power. And both the data and computational power are not easily available in many situations. So what transfer learning does for us is that it eliminates the need of extremely large data set. So we are going to need quite a bit of data if we want to work with deep learning, but we do not need huge amounts of data, and relatively less computational power will be employed, because essentially we are going to use pre-trained weights. And one thing we get with transfer learning is pre-trained weights. So we don't have to train the model to obtain the weights, and that makes life easier. And as you know, we are going to implement our pre-trained models in Python. And one of the things with that, and we are going to work with a practical example in the next lecture, is that the data must be in a specific format to be fed into the network chain. And for that, we are going to use something known as the image data generator. You'll see that further on. And there must be a main data folder. And inside that data folder, there must be a folder for each class of data containing the corresponding images. And that's exactly what we are going to see in the next lecture. But just to prepare you and acquaint you with some of these terms and file structures, and a couple of lectures ago, I had covered the importance of file structure and the folder structure to help us organize our data for real life applications. So it's exactly the same idea here. These are the dependencies that we'll use: pandas, numpy, keras layers, pre-processing image, import model, and so on. And we are going to see this in the next lecture, and you should be acquainted with these dependencies. And essentially this is the programming flow that we'll end up using. And again, we are going to have dense layers and activation functions like ReLU and so on. And this is just an example of transfer learning of mobile net in Keras. So we have the base model, which is mobile net, which we imported in. These are the weights. Weights are actually stored in this variable called ImageNet. And then we just continue by adding on our own layers and to the pre-trained mobile net model. And this is just another example. And other transfer learning models that have been commonly used with image data include things like ImageNet, Oxford VGG model, the Google Inception model, and the Microsoft ResNet model. And for language data, we usually have the Word2Vec and the GLOVE model. But of course, if you work with imagery data, then these are the transfer learning models that you can look into. And we have the same idea of an input layer, a convolutional layer, pooling layer, fully connected layer, and the output layer. And a lot of these things we'll get as a part of the transfer learning model that we select. Now, in the next lecture, we are going to work with something known as an Inception V3 model. And as you know, this is not the only model, but I think this is a pretty good model. It's an image recognition model, and it's built on Google's Inception architecture. It recognizes general objects of 1,000 classes, and what it does is it carries out feature extraction with convolutional neural networks, and then the classification is carried out with the fully connected and softmax layers. The feature extraction portion is used as a starting point, and layers to classify are retrained on the data set. And essentially, Inception model has 22 layers, but we don't have to build them from the scratch. This is the ResNet model, and it's a major breakthrough in the field of image recognition, and it's an extremely deep neural network with 152 layers. And this introduced something known as skip connection, which makes ResNet more powerful than things like Inception V3. And what does the skip connection do? It mitigates the problem of vanishing gradient by allowing this alternate shortcut for gradients to flow through, and it allows the model to learn an identity function which ensures the higher layer will perform as good as the lower layer and certainly not any worse. And this is the Word2 model, and we don't need to go into that. So basically, this is what transfer learning does. It'll allow us to use a pre-trained model and essentially feed our own data into it. And we'll work with a practical application in the next lecture.